According to this rule, more electronegative element or group not only prefers to stay, we have to compare the CH bond length, okay. Always remember, whenever you're removing two electrons, you have to remove the electron from the outermost orbitals, okay. Hello dear students, welcome to LN Overseas and welcome back to our series that is 45 important topics in 45 days, okay. As you know that this series is divided into three parts, 15 topics of physics, 15 of chemistry and 15 of mathematics, and I will be discussing this chemistry part, right? So today we are going to continue with our next topic, and that is MOT, dipole moment and Bend's rule, that is taken from the chapter chemical bonding. So today we are going to discuss these three topics, right? So let's start with the very first topic, that is Bend's rule. This is very important rule, and on the basis of this rule, question based on bond order, bond length, bond angles, bond strength, bond energy, such kind of very important questions are being asked in the exam, right? So that's why this topic is very important. So let's understand what this rule says, okay. So first of all, this rule is applicable for non-equivalent hybridization showing molecules. So first of all, the question is, what is non-equivalent hybridization? So if we talk about the hybridization, basically the sp3d and sp3d3. These are the hybridizations which are themselves non-equivalent in nature. Non-equivalent hybridization means where the hybrid orbitals are not equivalent to each other. Some hybrid orbitals will be having more percent s character, some will be having less percent s character. So these are the two hybridization which are themselves non-equivalent in nature. All the other hybridizations, the hybridizations are equivalent. But when in those hybridizations also, they can become non-equivalent when they have different surrounding atoms or when the central atom contains lone pair. For example, I have this molecule CH3F, okay, CH3F. So this is having sp3 hybridization, okay, sp3 hybridization. So in sp3 hybridization, we know all the four hybrid orbitals, when these are formed, they are equivalent in nature, okay. But when surrounding atoms are not same or central atom is having any lone pair, then the hybrid orbitals becomes non-equivalent. Means some hybrid orbitals will be having more percent s character and some will be having less percent s character, right? So in this category, what molecules we are going to include? First of all the molecules belonging to these two hybridization, and those molecules which are either having different surrounding atoms or lone pair on central atom. All these molecules will be included in non-equivalent hybridization, right? So this Bend's rule will be applicable only for non-equivalent hybridization showing molecules, right? This is one important thing. Now next point, more electronegative. According to this rule, more electronegative element or group not only prefers to stay in the hybrid orbital of central atom which is having less percent s character, but it also decreases the percent s character in the attached hybrid orbital of central atom. So first of all, this rule is saying that if you have a more electronegative atom, more electronegative surrounding atom, then that more electronegative surrounding atom will prefer to stay in that hybrid orbital of the central atom which is having less percent s character, right? This is one thing. And after occupying that hybrid orbital, it will try to decrease the percent s character in that hybrid orbital. So ultimately we can say that whichever hybrid orbital to which the highly electronegative element is attached, in that hybrid orbital, there will be less percent s character. This is one thing, right? Now the next, similarly, when we talk about lone pairs, so lone pairs increase the percent s character in the hybrid orbital of the central atom to which they are attached, okay. So for the lone pairs, first of all, they will try to occupy that hybrid orbital which is having more percent s character, and after occupying that, they will increase the percent s character in that hybrid orbital. So ultimately, we can say in whichever hybrid orbital the lone pair is present, definitely in that hybrid orbital the percent s character will be more, okay, comparatively, right? So these are the statements of Bend's rule. Now, how we are going to apply these, and on the basis of this, how we can compare the bond length, bond angle and other properties. So let's see. We are going to take few examples to understand this Bend's rule, right? So now, let's see. First of all, we have to draw the proper structure. Draw the proper structure of the given species. Now, what is the meaning of proper structure? We know whenever we try to make the structure, first of all, we find the hybridization, okay, and then on the basis of hybridization, we find out the electron geometry, and in that electron geometry, we try to arrange the elements, arrange the surrounding atoms, okay. But when we apply the Bend's rule, and we know if we talk about the hybridization in sp3d and sp3d3, I told you these are non-equivalent hybridization because they are having two types of positions. If you remember, in these hybridizations, you have axial and equatorial positions, okay, axial bonds and equatorial bonds, right? So when it comes to these hybridization, we have to decide where to place the more electronegative element and where to place the lone pair, okay, fine. So let's see. If we talk about this molecule, this is having sp3 dehybridization. It is having sp3 dehybridization, that is non-equivalent hybridization, and we know in this the electron geometry will be electron geometry is trigonal bipyramidal, that is TBP geometry, trigonal bipyramidal geometry. So if I will make making the structure, I will be making the structure, it will look like this: trigonal plane and two perpendicular bonds, okay. I know that these two perpendicular bonds are called as axial bonds, and these three trigonal planar bonds are called as equatorial bonds, okay. Now, in this geometry, the axial bonds are having less percent s character. Always remember, these axial bonds are having less percent s character as compared to equatorial bonds, right? So, if I want to place a highly electronegative element in this geometry, then I will place them at the axial position. According to Bend's rule, highly electronegative element occupies the less that hybrid orbital which is having less percent s character. So, less percent s character is present along the axial bonds. So, that's why highly electronegative element will be present at axial position. On the other hand, if I have to place the lone pair, then lone pair will be placed at equatorial positions, because comparatively the equatorial positions are having more percent s character, okay. So that's why in TBP geometry, whenever you have to place highly electronegative element, place it on the axial position and place the lone pairs along the equatorial positions, right? Understood? Now let's make the proper structure now. Now, I have 2 fluorine and 3 chlorine. So, I know fluorine is more electronegative as compared to chlorine. So, I will place the fluorine at the axial position. Now, the remaining chlorine will be placed at equatorial positions. So, this is the proper geometry, proper structure of this molecule following the Bend's rule as well, right? Now, let's see the next molecule. Next is PF3Cl2. So, this is also sp3d hybridization. So, again we have the TBP geometry, okay, TBP geometry. So, we have 3 fluorine atoms now, 3 fluorine atoms. So, first of all, we'll place the 2 fluorine atoms at the axial position. Now, for the third fluorine, we don't have any other option because only equatorial positions are left. So, the third fluorine will be placed at equatorial position only, right? And the 2 chlorines also at the equatorial position. So, this will be the structure. So, first of all, you will give the priority to the more electronegative element. You will place them at axial position, and whatever elements are left, you will place them along the equatorial position, right? Now, let's see the next example. SF2Cl2, this SF2Cl2 molecule, here the sulfur is having a lone pair. So this is also having sp3d hybridization and TBP electron geometry. So now let's make this structure. This is the TBP geometry, right? So again we have fluorine. So fluorine will be placed at axial position, okay, and chlorines will be placed at equatorial. Now we have one lone pair. So we know in TBP geometry we have to place the lone pair along the equatorial position. So here we are going to place the lone pair along the equatorial position, okay. So this is the proper geometry of SF2Cl2 molecule. Similarly for ICl2 minus also. ICl2 minus also having the same sp3d hybridization, and the geometry, electron geometry will be TBP, right? So we have chlorine, 2 chlorine atoms, right? These are the only 2 surrounding atoms. So first of all we are going to place them at axial position, right? And here on this iodine there will be 3 lone pairs, 1 negative charge, so there will be 3 lone pairs on the iodine. So those 3 lone pairs we are going to place them along the equatorial positions, right, like this, okay. This is having negative charge. So this will be the structure. And if we'll talk about the shape of this molecule, shape of this molecule is linear. Shape of this molecule is linear. Similarly, the shape of this molecule will be seesaw shape. This is called as seesaw shape, okay. So this is how we can make a proper structure of a molecule following the Bend's rule, right? Now let's see the next question. Now if you have to compare the bond length, and you have to find out the bond length order, then how you can find out following the Bend's rule also, okay. So let's see. Here we have this molecule CHCl3. So first of all we are going to make this structure. 1 hydrogen and 3 chlorine atoms. Here you have CHF3, 3 fluorines, okay. And we have to compare the CH bond length, okay. Which CH bond will be longer or shorter, right? So let's see, okay. Here we know that fluorine is more electronegative as compared to chlorine, right? Fluorine is more electronegative as compared to chlorine. So we know that more electronegative element decreases the percent s character in the hybrid orbital to which it is attached. So these fluorines are attached to these hybrid orbitals, these 3 hybrid orbitals, this one also, right? So in these hybrid orbitals to which they are attached, they are going to decrease the percent s character. So we can say here it will be less percent s character. In these 3 bonds there will be less percent s character due to these more electronegative elements, fluorine, okay, fine. So if these 3 hybrid orbitals are having less percent s character, then the opposite, the other hybrid orbital that is present here in this CH bond, that is making the CH bond, this hybrid orbital will be having comparatively more percent s character, because the total s character is fixed for the whole molecule. So if these 3 are having less percent s character, the opposite will be having consequently more percent s character, right? And always remember how to compare the bond length with percent s character. Bond length is inversely proportional to percent s character. Inversely proportional to percent s character. As the percent s character increases, bond length decreases, because when percent s character increases means it becomes close to the nucleus and the atoms will come more close to each other, the attraction will increase, so bond length will ultimately decrease. So these are inversely proportional, right? So this bond will be shorter as compared to this, because here the surrounding atoms are chlorine, which are less electronegative. So here in these bonds comparatively more percent s character, and here in this CH bond there will be comparatively less percent S character. In this CH bond comparatively less percent S character, right? Less percent S character means the bond length will be longer, bond length will be more. So that's why in the first case, the CH bond will be longer as compared to the second case, okay? So you don't have to solve for both molecules. You can just pick one molecule where either you can see more electronegative elements or lone pair, okay? Just pick that molecule and solve accordingly. If you are getting more percent S character for this one, then obviously comparatively here it will be less. So this bond length will be shorter and consequently the other will be longer comparatively, right? Similarly, let's solve this one question more. Here you have CS3Cl. So Cl bond. Now we have 3 hydrogens on carbon. Here we have to compare the CCl bond length, okay? And here CCl. Now in place of hydrogens you have fluorine. So the same concept will be applied here also. Fluorine is more electronegative. So more electronegative means less percent S character. Less percent S character. So in these 3 bonds, if there is less percent S character, then in this opposite bond there will be more percent S character. More percent S character means shorter bond length. Shorter bond length, okay? Shorter bond length. So we can say we are going to get the decreasing order for this order also, okay? For these molecules also. Fine. This is how we can compare the bond length on the basis of Bend's rule, right? Now, let's see another application of the Bend's rule, that is bond angle order. Now we have to compare the bond angle of these molecules. So let's see how we can compare the bond angle following the Bend's rule. So here you have NH3 and NF3. So first of all, let's make this structure. 1 lone pair on the nitrogen, 3 hydrogen. Similarly, here also 1 lone pair on the nitrogen and 3 fluorines. 3 fluorines, okay? So we have to compare the bond angle. So let's say this bond angle is θ1 and let's say this bond angle is θ2. So we have to compare the bond angle θ1 and θ2, right? You can see that lone pair is common in both the cases. So you cannot decide on the basis of lone pair. So we have to decide on the basis of surrounding atoms. Surrounding atom, here you have fluorine, here you have hydrogen. So we know fluorine, again, more electronegative element. More electronegative element. So less percent S character. Less percent S character in these bonds. So these 3 bonds, these 3 hybrid orbitals will be having less percent S character, okay? Now you have to remember this point whenever you are comparing the bond angle between the bonds which are having less percent S character, that bond angle will be less comparatively compared to this molecule. In this molecule you have hydrogen. Hydrogen is less electronegative. So comparatively these bonds, comparatively these hybrid orbitals will be having more percent S character. Comparatively more percent S character. And whenever you are comparing the bond angle between the bonds having more percent S character, that bond angle is always greater as compared to the bond angle which is formed between bonds having less percent S character, okay? So from that I can say θ1 will be more. θ1 will be more as compared to θ2. More percent S character, more the bond angle, okay? So θ1 is greater than θ2. This is how we can decide on the basis of Bend's rule, okay? And one more thing I should tell you, here you can see that steric crowding, steric factor is not applicable for hydrogen and fluorine. So when steric factor is not applicable, then only you will apply the Bend's rule, okay? Whenever steric factor is there, you have to decide on the basis of steric factor, right? Now, let's see another example. Okay, here you have OF2. So this is again the similar case. Oxygen is having 2 lone pairs. Here in water also, oxygen is having 2 lone pairs. 2 lone pairs, okay. And lone pairs are common in both the examples. So we have to decide on the basis of surrounding atom. So surrounding atom, fluorine is more electronegative. More electronegative. That means less percent S character. Less percent S character. And here comparatively these bonds will be having more percent S character, right? So the angle between the bonds having more percent S character will be more as compared to the angle which is formed between bonds having less percent S character. So this angle will be more. This angle in water will be more as compared to OF2, right? So we are going to get the increasing order, right? And here also steric crowding factor. Steric factor is not applicable for the hydrogen and fluorine. So here you can apply the Bend's rule, right? This is how applying the Bend's rule you can find out the bond order, bond length, bond angle, bond energy, these properties, right? This is how you can apply. Now, let's move forward. Let's see the next topic of this chemical bonding, that is dipole moment. So first of all, let's see what is dipole moment. Dipole moment is the product of charge accumulated on an element and internuclear distance. So how mathematically we can define it? Dipole moment is the product of charge into bond length, distance between the nuclei, that is called as bond length, right? So one more thing, it is a vector quantity whose magnitude is Q into D and direction is from positive to negative. Okay, so this is the formula for the dipole moment. Mu theoretical is Q into D. So dipole moment is represented by the symbol mu. Okay, and Q will be the charge accumulated on the species, D will be the bond length, distance between the nuclei of the two atoms, right? And the unit of this is Debye. And as written here, it is a vector quantity. So it will be having a direction. So what will be the direction? It is always from positive to negative. Positive to negative, or we can say less electronegative element to more electronegative element. Fine. Now, mu TH means theoretical dipole moment. Q is the charge accumulated on either A or B. Suppose I have this molecule A and B, where B is more electronegative. Where B is more electronegative. So we know more electronegative element attracts the electron, bond pair electrons toward itself. So it will gain a partial negative charge, and consequently the opposite element will gain a partial positive charge, right? So this is the charge accumulated on the species, and this is the bond length, right? And now if I want to find out the direction of dipole moment, what will be the direction? From positive to negative. This will be the direction of dipole moment, right? Okay. So charge accumulated either on A. You don't have to add these charges. Either you can take the charge of A or B without sign. You don't have to apply the sign. You just have to take the magnitude, right? And D is the bond length of AB. Now, the unit of mu is Debye, we know. Now, 1 Debye is equal to 3.33 into 10 is to the power minus 30 coulomb into meter. And in ESU centimeter, it will be 10 is to the power minus 18 ESU centimeter. And the value of Q will be taken as 1.6 into 10 is to the power minus 19 coulomb. And you can take this value when the charge Q is either plus 1 or minus 1. Okay. When the magnitude of charge is either 1 or plus 1 or minus 1, you can take that value 1.6 into 10 is to the power minus 19 coulomb. Okay. Now let's see the question related to dipole moment, how we can find out that the molecule will be polar or non-polar. Okay, that is the application of this dipole moment. We have to find out the polarity of the molecule. So how to find out? We are going to make the vector, dipole moment vector for each and every bond present in the molecule. Then for the whole molecule, we will see the mu overall, means mu net. What is the total sum of these all dipole moment vectors? Basically here you don't have to find the actual sum, the value of the vector addition. You just have to find out that it will be 0 or non-zero. If the mu overall is 0, then we will say that the molecule or the species is non-polar. Okay, but if mu overall is not equal to 0, then we will say the species is polar. This is how we can find out. So let's see these examples. You have AlCl3. So first of all, you have to make a proper structure. After making the proper structure, then only you can find out the right answer. So this is the proper structure of AlCl3. First of all, I am making all the structures of these molecules. This is PCl5 and you have SF6. SF6 is octahedral geometry where 4 fluorines are present in the square plane. 2 are perpendicular to this square plane. Okay, this is the structure. Now you can see one thing, that all these 3 geometries are perfect geometries. Perfect geometries means there is no lone pair on the central atom, no lone pair on the central atom, and all the surrounding atoms are also same. So when you have these kinds of perfect geometries, then the mu overall for such species, will be 0. You don't have to calculate it, it will come out to be 0. Okay, because there is no lone pair on the central atom and all the surrounding atoms are also same. So when you will find out the mu overall by drawing all the dipole moment vectors, so the sum of all the vectors will come out to be 0. Just like here in this one also and in the third one also, whenever you have the perfect geometries, the sum of all the dipole moment vectors will be 0. That's why mu overall is 0. Mu overall 0 means these species are non-polar in nature. These species are non-polar in nature. Fine. Now let's see few more molecules. Okay, these are the molecules. First of all, you have XeO2F4. XeO2F4. So let's draw the structure of this molecule. Okay, here you have 4 fluorines. This will be the octahedral geometry. 4 fluorines, double bond O, double bond O. This is the geometry of this molecule, structure of this molecule, proper structure of this molecule, right? Now you can see, even after having different surrounding atoms, the mu overall will come out to be 0 for this structure because these 4 fluorines are present in the square plane. So the vectors of these 4 fluorines will cancel out each other's effect. Similarly, the vector which is above the plane for the above oxygen and the below one, they are going to cancel out each other. So mu overall will come out to be 0. Okay, let me make this dipoles. This is this one and this one, they will cancel out each other. Similarly, this one and this one, they will cancel out each other, and this one and this one, they will cancel out each other. Okay, or where always remember the direction of dipole moment will be from less electronegative to more electronegative. Okay, so here you can see all the dipole moment vectors are cancelling out each other. So mu overall will be 0. That means this is also non-polar in nature, Okay, now the next one, SO2Cl2. SO2Cl2, what will be the structure of this molecule? So let's see. Here you have 4 sigma bonds, so sp3 geometry, sp3 tetrahedral geometry, sp3 hybridization, Cl and Cl. Okay, this is the structure of this molecule. Now if we make the dipole moment vector from sulfur to oxygen, less electronegative to more electronegative, sulfur to chlorine, okay. Now you can see this is a tetrahedral structure and surrounding atoms are also not same. So these vectors, they can never cancel out each other's effect completely. So the mu overall for this molecule will not be equal to 0. That is a non-zero value. Non-zero value means we can say that this molecule will be a polar molecule. This molecule will be a polar molecule, right? Now, these are also very important examples. Here you can see on the benzene, you have 2 hydroxy groups, dihydroxybenzene, and here you have 2 thiol groups, okay? So here what we can see, from this carbon to oxygen, this will be the dipole moment vector. Similarly, from this carbon to this oxygen, this will be the dipole moment vector, right? And for between OH bond, it will be from hydrogen to oxygen, and here also from hydrogen to oxygen. These are the vectors. Similarly, for this molecule also, from carbon to sulfur, and then hydrogen to sulfur, okay. Now you can see that these two vectors, they will cancel out each other, okay. For the carbon oxygen bond, they can cancel out each other, but these two bonds, the OH bond, the dipole moment of the OH bond, they are not cancelling each other. So that's why the mu overall is not equal to 0. Similarly, for this molecule also we can say mu overall not equal to 0, means these two are polar molecules. Okay, polar in nature, right? So this is how you can find out the polarity of a molecule based on the dipole moment, okay. Just calculate the overall dipole moment and find out that it is polar or non-polar, right? Now let's see the next topic. The next topic is molecular orbital theory, MOT, okay. So this molecular orbital theory says that when the atomic orbitals combine, they form molecular orbitals of two types, bonding molecular orbitals and anti-bonding molecular orbitals. So basically from this MOT, what kind of questions are asked in the exam? The question related to bond order, bond energy, the stability of molecule, such kind of questions are very common from this topic, right? So here in this MOT, basically when you make the MO diagram, you know that the energy of bonding and anti-bonding orbitals is different. So when you arrange them in the increasing order of energy, you get two types of orders. One order with the sp mixing and another order with which is normal without sp mixing, okay. So these are the two orders that I have written here, okay. This is the one order where you can see these molecular orbitals, these are the bonding molecular orbitals, and the ones which are having this asterisk mark, these are anti-bonding molecular orbitals, right? And similarly here, and this order where these pi 2px and pi 2py are having less energy, or we can say sigma 2pz is having more energy, this order is due to sp mixing, okay. And this order is applicable, for the species. This is applicable for the species which are having number of protons less than or equal to 15, okay. For example, you can take B2, C2, N2 molecules, etc. Okay. So this energy order will be applicable for the molecules which are having diatomic molecules which are having protons less than or equal to 15. Okay. For example, B2, C2, N2, etc. And this is the order which we are getting due to sp mixing. Okay. So sigma 1 is sigma star 1 is sigma 2 is sigma star 2 is pi 2px equal to pi 2py. Equal to means they are having same energy, equal energy. Sigma 2pz, then pi star 2px, pi star 2py, and last sigma star 2pz. Similarly, the second order, this is the normal order without sp mixing, and this will be applicable for species having protons greater than 15. Okay, greater than 15. For example, this will be applicable for O2 molecule, for F2 molecule, etc., which are having protons greater than 50. Now what we have to do, these are all the atomic molecular orbitals. So just like we fill the electrons in while writing the electronic configuration of any element, just like that we have to fill the electrons in this energy order of the orbital, starting from the lowest energy to the higher energy, right? So now let's see the question and let's see how we can apply this concept to solve the very important questions. So let's see this first question. The correct order of bond dissociation energy among N2O2 O2 minus is shown in which of the following arrangement? Okay, here we have to find out the order of bond dissociation energy for these three species, right? And this is a PYQ. So how we can find out? First of all, the bond dissociation energy. Bond dissociation energy is directly proportional to bond order. Directly proportional to bond order. Okay, so first of all we are going to find out the bond order, and on the basis of that we can find out the bond dissociation energy. Okay, so here you can see you have nitrogen and the two species are O2 and O2 minus. So we have to write those two energy orders for N2 and for O2. So let's see, for N2 what will be the energy order? It will be sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Okay, and here for N2 we know that sp mixing will be taking place. So pi 2px, pi 2py. Okay, and then you have sigma 2pz, then pi star 2px, pi star 2py, and at last you have sigma star 2pz. This will be the increasing order of energy for N2 molecule, right? Now for N2 how many electrons do we have? We have total 14 electrons. So we have to fill the 14 electrons now. So let's fill them. 2, 2, 2, 2. Okay, 8, and then these are 12, and here you have 14. So this is how we can fill the 14 electrons. Now how to find out the bond order? Bond order is having the formula 1/2 Nb minus Na. 1/2 Nb minus Na. Nb minus Na means number of bonding electrons minus number of anti-bonding electrons. So 1/2. How many bonding electrons we have? So count. 2 plus 2, 4. 4 plus 4, 8 plus 2, 10. So we have 10 bonding electrons minus anti-bonding. 2 and 2, 4. So only 4 anti-bonding electrons are there. So it will be 6/2, that is 3. So bond order of N2 is 3, right? Similarly, we can find out the bond order for O2 and O2 minus as well. So let's write the energy order for O2. Okay, let's write the order. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then you have now no sp mixing, so sigma 2pz, pi 2px, pi 2py. Then you have pi star 2px equal to pi star 2py, and at last you have sigma star 2pz, right? This is the increasing order of energy. Okay, fine. So for O2, how many electrons do we have? 16 electron, 8 plus 8, 16 electrons. So we have to fill the 16 electrons now. So let's see, 2, 2, 2, 2 and 2. So 10 are done, 2 and 2. Now 14, and this is 15 and this is 16 because they are degenerate. So we are going to fill 1 electron in these two anti-bonding orbitals, right? So now let's find out the bond order. Bond order equal to 1/2. Number of bonding electrons. So let's count the bonding electrons. 2 plus 2, 4 and 6, 10. Okay, so 10. 10 minus anti-bonding. 2 plus 2, 4. 4 and 2, 6. Okay, so this is 4/2, that is 2. So bond order for O2 molecule is 2, right? Now for O2 minus you don't have to write the complete order. For O2 minus you don't have to write the energy order again. In O2 minus you have to just add one more electron. It is having 17 electron. O2 is having 16, so this is having 17 electrons. So just one electron will be added. Now just see where you are going to add the next electron. The next electron will be added in pi star 2px, pi star 2py. So the next electron will be added up in the anti-bonding orbital. So bond order will be 1/2. The number of bonding electrons will remain same. The next electron that you are adding is coming in anti-bonding. So now the number of anti-bonding electron is changing. So now it will become 7, 1 extra electron. So this is 3/2. 3/2 means 1.5. So 1.5 will be the bond order for O2 minus. Okay. So now what is the order of bond order? Order of bond order is N2 having maximum bond order, then O2, and then O2 minus. Okay. That's why the order of bond dissociation energy will also be the same because both are directly proportional. So this will be the order of bond dissociation energy. So that's why here option 1 will be the right answer. Okay. Now similarly we will solve one more question. Okay. So let's see the next question. Okay. This is the next question. According to molecular orbital theory, C22 minus is expected to be diamagnetic. O22 plus is expected to have a longer bond length than O2. Okay. N2 plus and N2 minus have the same bond order, and He2 positive has the same energy as two isolated helium atoms. Okay. This is also PYQ, but this is a JEE Advanced question. JEE Advanced 2016. But you know, nowadays, such kind of questions are common in JEE Mains also. So that's why it is important for JEE Mains also. So let's see. Let's solve this question. Okay, first of all, it is saying that C22 minus should be diamagnetic. So let's see. For C22 minus, we have to follow the order of sp mixing. Okay, so let's write that order quickly. Sigma 1s, sigma star 1s, then sigma 2s, sigma star 2s. Okay, then you have, okay, after that you have pi 2px, pi 2py, then sigma 2pz, sigma 2pz, then after you have pi star 2px equal to pi star 2py. We don't have to write the complete order because we know we can fill the electrons in this order. C22 minus, so C2 is having 12 electron, 2 minus means plus 2, so 14 electron. So for C22 minus, you have to fill 14 electrons. So let's see, let's fill the 14 electrons. So 2, 2, 2 and 2 here and 8, okay, 2 and 2. So this is similar to nitrogen, similar to N2 molecule, similar to N2 molecule. So the bond order will be 1 by 2, and the bonding electrons, if we'll count, they will be 10, just like nitrogen, minus anti-bonding are 4. So the bond order is 3, but the option is saying that it will be diamagnetic or not. So you can see all the electrons are paired here. In each and every orbital, you have 2 electrons. So all the electrons are paired. Paired means diamagnetic. So that's why A option, the A statement is absolutely right. Okay, C22 minus is diamagnetic. Now let's see the next one. We have to compare the bond length of O22 plus and O2. So we have to write the energy order for O2. So let's write it. Okay, one more shortcut trick we can apply here, that this part is common for N2 as well as O2, like with sp mixing or without sp mixing, this part is common. And here you have 4 bonding electrons and 4 anti-bonding electrons. So they are like 4 minus 4, it is 0. Okay, so basically you can avoid this part to solve the question quickly, right? So we can avoid this part. So after this, we can write the order for O2. So now this part will remain constant. So I will be writing the order from this. Okay, so I know after this I have sigma. After these 4 molecular orbitals, we'll have sigma 2pz for O2. After sigma 2pz, you have pi 2px equal to pi 2py. Okay, then you have pi star 2px, pi star 2py, and at last sigma star 2pz. So this is the remaining order, and don't worry, the bond order value will also be same, don't worry. Okay, so now let's fill the electrons. So 4 electrons are already filled. Okay, sorry, not 4, 8 electrons are already filled. Okay, for O2, how many electrons we have? 16. So now we have considered that we have filled the 8 electrons already. So how many are left? 8 are left. So let's fill the 8 electrons. So 2, 2 and 2, 6, 1 and 1. Okay, so this is for O2, and now we can find out the bond order as well. So let's find out the bond order. Bond order of O2 will be 1 by 2. Now from this part also we are going to get the same bond order. So let's see how many bonding electrons we have. 6 bonding electrons. 6 minus anti-bonding are 2. So 6 minus 2, 4. 4 by 2, 2. So 2 bond order, that is the same, right? Now for O2 2 plus, you don't have to write the energy order again. We just have to remove 2 electrons. So Always remember, whenever you're removing 2 electrons, you have to remove the electron from the outermost orbitals, okay, which are having maximum energy. So for O2, the outermost or the orbitals which are having the maximum energy, highest energy, these are the pi star 2px and pi star 2py. So we are going to remove these 2 electrons. So 2 electrons are removed from the anti-bonding. So now what will be the bond order? 1 by 2, 1 by 2 into. Now only 6 bonding electrons are left, 2 plus 2 plus 2. In anti-bonding it is 0 according to this order, okay. So this will be 6 by 2, that is 3. So bond order of O2 plus is 3, right. So if I will compare the bond length is inversely proportional to bond order. Inversely proportional to bond order. So what will be the order of bond length for these species? I can say that, okay, O2 plus is having more bond order, so the bond length will be shorter for O2 2 plus. So this order we are going to get for these species. And in the option it is given that O2 2 plus is expected to have longer bond length. So this is incorrect. It is having shorter bond length as compared to O2, right? So B option is incorrect. Now in the C option you have N2 plus and N2 minus, which are having same bond order. So let's find out. Okay, now you don't have to write the energy order again, because we have already written for the sp mixing, we have already written this bond order. And for N2, for neutral N2, we know for N2 having no charge, the bond order is 3, okay. Just like C2 2 minus, this bond order is same. This is same for N2 as well, because N2 is also having 14 electrons, right? So this is already written here. So now we can solve this directly. For N2 the bond order is 3. So for N2 plus, what will be the bond order? For N2 plus the bond order will be 1 by 2, okay. So in N2 plus you are removing one electron from the bonding, okay. So bonding, so in place of 10 now you will be having 9 bonding electrons. Now anti-bonding electrons will remain same. So 5 by 2, that is 2.5, fine, 2.5. Now similarly for N2 minus means you are adding one electron, you are adding one extra electron. So that extra electron will be added in, okay, let's see, in anti-bonding orbital, in anti-bonding molecular orbital, right? So bonding electrons will remain same, that is 10. In anti-bonding now you have 5. So it is again 5 by 2, that is 2.5. So yes, we can say that N2 plus and N2 minus, they are having same bond order. So yes, option C is also right for this question. Option C is also right for this question, right? Now the last option D, He2 positive has same energy as 2 isolated helium atom. So for this also we have to find out the bond order of He2 positive. So let's see. If we talk about He2 positive, means how many electrons it has? Helium is having 2 electrons, so He2 will be having 4 electrons. But positive means 3 electrons. So we have to fill 3 electrons. So sigma star 1s. Okay. This will be having 2 and this will be having 1 electron. So bond order equal to 1 by 2. Bonding electrons are 2, anti-bonding is 1. So it will be 0.5. So He2 positive is having some bond order 0.5. So this cannot, the energy of this species cannot be equal to 2 isolated helium atoms, because isolated helium atoms are having no bond order. For them the bond order is 0. So if you are converting 2 isolated helium atom into He2 positive, means some energy change will be taking place in that process, right? So energy of He2 plus cannot be equal to the isolated helium atom. That's why D option is also incorrect, right? So that's why for this question, option A and option C are the right answer. Fine. So that's it from my side on this topic. We'll be continuing this series, so stay tuned with us and don't forget to watch the complete series. The playlist link is given in the description below, and do write your queries or suggestions in the comment box. We will surely revert you back. Fine, so stay tuned with us. Thank you.